All right, so this video is for properties and reactions for aromatic hydrocarbons. So the first thing we need to know, just these basic properties. They are nonpolar molecules. They would have London dispersion forces attracting them then. Since they are at least 6 carbons, and because of the fact that they lay flat, they usually are liquids or possibly even solids at room temperature. And toluene is used as a solvent, right? Because you can dissolve other nonpolar molecules in these things because they're nonpolar, right? I talked about this on the last one. Toluene is a special name that we need to know that has essentially replaced benzene as a solvent because we know that benzene can be toxic, that it can be a carcinogen. So we don't want to have those issues, so we use toluene all the time. That's why you have to remember that methylbenzene is called toluene. So make sure you keep that in mind. But otherwise, the main purpose of this video is to deal with the reactions for aromatic hydrocarbons. And it's not really that difficult. I don't have any addition reactions because there aren't any double bonds. Remember, they move. So I don't have a static double bond to add across. So instead, we're going to do these substitution reactions. Couldn't read there for a second. So these are weird, but they should be relatively easy because you can look at your notes and just follow the example. So obviously you need an aromatic ring in here. So I'll draw one of those real quick. And you're going to have some kind of alkyl halide, which means that I have a carbon chain that has a halogen on it. So this is a 2-chloropropane, right? So we should know what this is. We can name it on the test if we want to. But otherwise, when you're doing this reaction, all that happens is, remember, every carbon on the ring already has one hydrogen. And I'm just going to replace that hydrogen with my carbon chain that's hanging off of this chlorine. Now you should recognize that chain, in this case, looks like an isopropyl. So if I replace this hydrogen with an isopropyl, I have this new product over here. So I got my ring, and I put an isopropyl on it. But then that hydrogen replaces the isopropyl and is now attached to that chlorine. So I have an HCl byproduct. So I just flip-flop those two things. So this is how I build onto an aromatic ring and create something new. I just mix that benzene with whatever I want to attach to it, some alkyl halide that has that R group that I want attached. As long as I have this aluminum chloride catalyst, this should work. But it's relatively easy when it's all said and done. So I'm just going to put a branch onto the ring, right? This is now called an isopropyl benzene, right? But should be a pretty easy reaction. Halogenation, similar, right? If I have a ring to begin with, and this time I'm going to make it a toluene, and I add some kind of halogen. This is a lot like what we did before, right? The very first kinds of reactions that we did, we replaced hydrogens with fluorines. And what we're going to do is replace any of the hydrogens that are left on the ring, specifically on the ring, because there are also hydrogens on this methyl up here. But there's only these 5 hydrogens on the ring that I can replace with the fluorine. So when it's all said and done, I want to replace any one of those with a fluorine, which in this case would be ortho in position to my methyl. So this is a orthofluorotoluene. But you also have to recognize that I also could have had a metafluorotoluene, because this and this would be different from each other. Attaching to those different places on the ring and even this other place, right? I should have O, M, and P options for my product over here. So I need to draw all 3 of those, right? There should be an orthofluorotoluene. There should be a metafluorotoluene, and there should be a parafluorotoluene. So if there's already a branch, if it's a toluene, I have this situation. Remember the last reaction, I didn't have that problem. but that's because there wasn't anything on the ring, so all of the carbons were equal to each other. So in both cases, whether it's the alkylation, like this slide, or if it's the halogenation, you can technically end up with 3 different products, but you have to have something on the ring already for those OMP products to emerge. The other thing that I'm going to need here, again, there actually are 2 fluorines here, so that hydrogen that I replaced ends up with one of those fluorines and hydrogen fluoride byproduct here. So make sure you have that as well. But I should have those or 1, 2, 3 options with that hydrogen fluoride. Nitration, again, go back to a simple benzene ring here because I don't want to make this too crazy. Or maybe I will make this one have the toluene because this one I can actually name. So I have an aromatic ring here, toluene, and I have nitric acid. And I'm going to react these 2 things to make a nitrated aromatic ring, right? What's going to happen here essentially is kind of like the last one. I'm going to take a hydrogen off of this ring, right? And I'm going to take 1 hydrogen from here and 1 of these 3 oxygens. So I'm going to take 1 oxygen, which leaves 2 when it's all said and done. So I don't have this hydrogen anymore. I don't have 1 of those oxygens, but 2 hydrogens and an oxygen are going to make a water byproduct, that water that's up here. So I'm going to take out a water, and what I'm going to leave behind on the ring is a new group, this NO2, that we're actually going to call a nitro, right? So a new thing, you can name this. Again, naming products always gives you bonus, so you're going to want to try and do that. This is actually called a nitrotoluene. And it would be an O-nitrotoluene, which means that there obviously should be 2 other versions of this, because I should have an O, an M, and a P byproduct. So make sure that you have all 3 in your notes. I'm only going to draw this one because I'm pretty sure you know how to draw the other ones. But otherwise, this is a new thing that we know how to name. This is my nitro. And just like anything else, we learned fluoro, chloro, iodo, bromo, right? This is nitro now, right? That's what you're going to name this as your branch. But it was a toluene because there's a methyl there. Otherwise, if there was no branch, if it was a benzene, I'd only have 1 product. So it's a little bit weird. Again, it may help if I showed you what nitric acid looks like otherwise, because if I have this drawn out, you might be able to tell how I can take this hydroxide and a hydrogen to make a water. Otherwise, there's also another oxygen on here that just happens to look a little weird because it's going to be a little weird. But these electrons may or may not be in a pair on this oxygen, or there might actually be a bond right here between the oxygen and nitrogen. But either way, that's weird. Something that you're not really familiar with. But technically, when I'm taking that hydrogen and oxygen, it's in a hydroxyl group already. So adding a hydrogen to that to make water is pretty easy. So otherwise, that may have confused you more than it helped you. But again, if you see this, you put a nitro on the ring. That's all you really need to know. My last reaction is this sulfonation. This one I'm only going to do 1 version. I'm probably going to do the same thing on the test because I'm not even sure how to name the other versions. So I'm not going to expect you to know how to do it. So I have this SO3. And I have an aromatic ring, a benzene here. I have a sulfuric acid catalyst. All of these have catalysts. Remember to look out for those. Otherwise, I'm going to make this sulfonated aromatic ring, and there's no other byproduct. So what you have to realize here is that I'm going to take everything that's here stays here. So technically, I'm going to try and replace a hydrogen here, but that hydrogen has to go somewhere, right? So what I'm going to make here right? It's going to look weird. It's going to go SO3 and then there's going to be an H behind it possibly, right? Which I prefer a different look for that because I just don't really like how that looks. It actually would look more like this, which may or may not be better for you. But this is what we're going to call sulfonic acid, which I may have to check on the spelling of this later, but sulfonic acid, right, is my product here because I had 3 oxygens, right? You can still see the 3 oxygens, but one of these hydrogens was replaced, but it actually was transferred to this SO3, this sulfur trioxide, before that was added onto the ring. So it's still here, it's over here. And the reason I like this look is because this sulfuric acid that is actually the catalyst for the reaction to begin with looks like this if I draw it out, right? So I can see how this sulfonic acid can be acidic, literally, when it looks a lot like sulfuric acid up here, right? So I like to draw it out this way. If you did that SO3 with an H, that actually isn't technically wrong. I just don't really like the way it looks. I like it to look like this so I can tell that it's an acid, just like that sulfuric acid that was my catalyst to begin with. This is this H2SO4 just drawn out so you can see the molecule and what it looks like. So that is an acid, literally. So is my byproduct, or so is my product down here. It's called sulfonic acid. So again, if I have to check the spelling later and tell you guys I did that wrong, that's fine. But otherwise, you should know how to do all of these reactions and just use examples from your notes, right? I can put a branch on a ring using this alkylation. I can add a fluorine anywhere I want on a ring with halogenation, or it can be a chlorine or a bromine or an iodine, right? I'm adding a halogen. Nitration, I add this nitro group that we just learned about, right? That also could be drawn funny and different, but you know, you can see it right here technically. This is what it would look like hanging off of that ring. But finally, that sulfonic acid, that's all you're going to need to know.